Good evening, everybody. Good evening, viewers. Welcome on Science Minds Talk. और आज जो है हम लोग एक इंटरेस्टिंग सब्जेक्ट पे बात करने वाले हैं and we've got two great luminaries with us. We are talking on neutrinos today. ये न्यूट्रिनोस का विचार कहाँ से आया कि हम लोग रेगुलर जो है on a regular basis we invite experts, scientists, doctors to talk on various topics and there is always a conversation between two experts, two people who know the subject. इस बार हम लोगों ने फॉर्मेट थोड़ा चेंज किया. It all started because एक न्यूज आइटम आई थी कि इंडिया will lose its edge अगर न्यूट्रिनो रिसर्च के लिए जो है अगर तमिलनाडु का कोई प्रोजेक्ट है which gets delayed by 1 year, we lose our edge. Now that got us thinking, worried कि what is this all about. तो थोड़ा सा हम लोगों ने R&D किया और we got in touch with people. So we'd like to welcome our the guests of today, Professor Vivek Datar and Dr. Satyanarayana.
Hello.
Welcome, sir. Welcome, Vivek, sir. Welcome, Satyanarayana, sir.
Thank you.
And we've changed the format a bit कि इस बार जो है कोई expert सवाल नहीं करेगा. It will be like I am a non-science person with an interest in science. So I got an outside view. The two experts are there who are thick in the middle of it. And then we've got a bunch of students, very curious, inquisitive students from mostly from North Bengal. So we have a bunch of students who are very keen. So we invite the students also. Let's let them just say hello to everybody. And then we get into the discussion session after that. That's Pratyusha Burman from Modi Public School, Siliguri.
Yeah. Hi. Hi.
Hello, everyone.
And also Barishan Ghosh from Modi Public School, Siliguri. And we got a one of the partners on this today's talk show is an organization called SWAN, Sky Watchers Association of North Bengal. This is primarily they indulge in astronomy, but their whole range of activities is into practical science, into for amateurish activities taken to professional levels. So that's that's a wonderful organization that whole of India should know about these people. And we would have got two young boys from there, Janmejay Sarkar and Shubhamay. Saurabh Go from there. So primarily, इन्होंने question answer session set किया. So let's set the ball rolling now. So welcome children, welcome professors. Let's start the talk. This news came up that India will lose its edge over rivals in neutrino project if delayed by another year. That set us very interested in what this is all about. So let's for a lot of people who are from the non-science background, sir. Let's start with what exactly is a neutrino. Can we have a brief introduction to that?
Yes. So the neutrino is a fundamental particle like the electron.
Okay.
We all know about the electron, which is part of the atom and molecules and so on.
Yes.
The electron is a charged particle. It's fundamental because you cannot break it up and make two halves of electron, for instance. So there are many such elementary particles, the so-called leptons, which are electron, muon, and tau particle. And each of these particles has a corresponding particle called the neutrino.
Okay.
And these neutrinos participate in the so-called weak interaction. There are four interactions in nature that we know of. Two of them have been unified, the electromagnetic interaction and the weak interaction. Electromagnetic interaction, as you all know, is responsible, for instance, for our communication today. Just now we are communicating through the electromagnetic interaction, through wireless transmission, through, or maybe through cable and so on. So electromagnetic interaction is the most commonly used and well-known interaction. But the weak interaction is it goes by the name weak. So it's much weaker than the electromagnetic interaction by about 12 orders of magnitude in strength, weaker than that. Of course, there is another interaction which is even weaker, but which we have all heard about from school days. And that's the gravitational interaction. Gravitational interaction is another 25 orders of magnitude weaker than the weak interaction itself.
Okay.
But it grows with mass. It's proportional to mass and so on. So that's why the Earth rotates around the sun and so on. And okay, so the neutrino interacts only weakly, and now as it, of course, anything that has energy can interact gravitationally. That we now know. Photons also interact gravitationally. They can bend, for instance. The sun bends the light of a object which is behind it. So there is so-called gravitational lensing and so on. Okay. So the neutrino is also another. I mean, since it's part of the weak interaction, it is absolutely crucial in the first fusion reaction that is part of the chain of fusion reactions that go on in the sun and give us light. Okay. So two protons combine to form a heavy hydrogen, deuterium, plus a positron, which is the antiparticle of the electron, and the neutrino. If this reaction were not there, the sun would have died in the course of a few days. Because of the weak interaction, it has lived for so many billion years, and it will live for another 4 or 5 billion years at least. Okay, so that's the. I don't know if I've given some idea of what the neutrino is. It's a very light particle, something like a millionth of the mass of the lightest elementary particle that we know, which has mass, which is the electron. And this is about 1,000,000 times lighter than that.
Million times lighter than the electron.
Pardon?
Yes.
Million times lighter than the electron.
Correct. Yes.
Yeah. And we've also read that almost 1,000 trillions of them are passing through our body every second.
Yes. That is because, as I said, the sun is producing energy through the fusion reactions. And the sun produces lots of neutrinos. And in fact, if you just put up your finger, the tip of your finger, which is roughly a square centimeter in area, through that, there are about 60 billion neutrinos passing every second. And you won't come to know of it because it's a weakly interacting particle. It'll just, in fact, the solar neutrinos, the sun's neutrinos, pass through the Earth with just like extremely transparent glass, as light would pass through extremely transparent glass. It doesn't interact, even if it passes through one whole diameter of the Earth.
Okay. So, I mean, each and everything that you say raises several more questions, but we get on to the children now. Pratyusha Burman had a very interesting question on the discovery of, we have Barishan Ghosh. Let's start with Barishan Ghosh. Barishan, you had a very interesting question on when the neutrinos were first discovered. So why don't you talk now and ask sir about your query?
Okay, so the neutrons were first theorized when we found out that when a particle breaks off into a beta particle and another atom or element, then the combined mass of the beta particle and the particle does not match the weight of the original particle. That was explained by a neutrino. But since we already said that neutrinos are extremely, like 500,000 times less than the mass of an electron, and we have so much difficulty measuring the mass of an electron even. So how did we go as far as to understand that it was actually a different particle that we never know of and we cannot detect, and not that our instruments were like wrong at measuring?
You mean to say, how was it detected in the first place?
Pardon?
How was it detected in the first place? Such an illusion. Yeah.
Okay.
Yes, sir.
So, of course, since in beta decays, which were seen in cloud chamber photographs, what was the beta particle, of course, can be seen in the cloud chamber because it leaves a track. Similarly, the recoiling nucleus, the daughter nucleus, also leaves a track. But there, as what is his name? Just now, the
Harshan.
Harshan. Okay. So as he said, sorry, I'm not getting your name. Ghosh. I'll just call you Ghosh.
Ghosh.
Okay, Barishan Ghosh. So since the two energies did not add up, because we know the masses, these were measured by Aston in the mass spectrograph. And of course, using E equal to mc squared, you know the energy to start with, which includes the mass energy also, mass energy relation. And then the final nucleus and the beta particle. And the beta particle was found to have a continuous energy distribution. So sometimes it would have, very little energy. Sometimes almost all the energy that could be taken away as per the difference of masses times c squared. So this was a puzzle because it was known by that time that atoms exist in quantum states, so they have definite energies. So why is it that sometimes you get this energy, sometimes that energy? Is it that the law of conservation of energy is not valid? So Pauli somewhat unwillingly proposed that there be a particle which carries away the missing energy. And now, of course, if since it does not leave a track, that means it has to be uncharged. Also, from angular momentum considerations of the initial and final states, he immediately concluded that that particle has to have spin half. And of course, so it has to carry away energy and therefore momentum. And that's not a problem because you can conserve energy momentum this way once you have a third particle in the final state. And also, it has spin half, so you can conserve angular momentum. So now the fact that it has small mass was also concluded because the beta particle sometimes has the maximum energy that it can have. Okay, so that means that at that time the neutrino carries away very little energy. So obviously, if its mass is high, then that cannot happen, and therefore its mass has to be small. In fact, Pauli already said that this has to be about 1/10 or smaller in mass as compared to the electron. But now, of course, we know that it is more than 1,000,000 times or of the order of 1,000,000 times smaller in mass. How was it detected? Okay, since it doesn't have a charge, you have to have some interaction by which it gets detected, and that is through the weak interaction. So just as the neutrino is emitted in beta decay, you take the inverse process. So the neutrino interacts with the daughter nucleus, then you will get a positron and a final nucleus in the final state. Okay, so that's the reaction that was used. You have to have a very strong source of neutrinos, and you have to have a very large detector because, as I said, the neutrino interacts very poorly with matter. Okay, very weak interaction. So, of course, this was done in a reactor experiment. In reactors, you get, if you have a let's say, gigawatt reactor of the type, for instance, that we have in Kudankulam, which is producing energy, then that produces about 6 times 10 to the power of 20 neutrinos per second. 10 to the power of 20 is some mind-boggling number, right? We can't imagine it. But that's a very strong source of neutrinos, and that was used in the first detection around 1956 or so, 1956. Reines and Cohen made the measurement in a so-called Savannah reactor in the US. Almost 26 years after it was predicted.
Yeah, almost 3 decades.
Yeah, that's right.
Yeah.
Okay. So since we are on this, the discovery of the neutrino, and we have another question again by Barishan. Barishan, I like both of your questions, and why don't you talk about the proof of about the splitting of few atoms in the vat of argon? That was also a very interesting question. So just continuing with the same topic that we are here, you can please continue the next question also.
Okay, so I read that neutrons were first discovered when like some scientists basically took this huge vats of argon or chlorine, and then when the neutron hits an atom of argon or chlorine, it splits into a beta particle and a different atom. So how, like, these were millions and billions of atoms in a vat. So how did we detect that single atoms, like in a whole week of operation there will be 3 atoms? How will we detect that?
Yeah, so let me tell you, this was actually a 600-ton, of so-called cleaning fluid, which is C2Cl4. So it didn't have argon to begin with; it had only chlorine, and the isotope of interest in that was 37 chlorine. So when you do your chemical equations and calculate things in chemistry, you know that the mass of chlorine is taken to be 35.5. Why is that? Because there are 3 times as many atoms of mass 35, chlorine 35, as compared to chlorine 37. Okay, so chlorine 37 is 1 out of every 4 atoms of chlorine. That's the so-called natural abundance. Now, when a neutrino from the sun comes, it interacts. Of course, not all neutrinos interact, by the way. Not just because the probability of interaction is very small. Also because they come with all sorts of energies, and only those neutrinos which have energies above about 850 keV, they can produce this reaction. So they interact with the chlorine 37 to give you argon 37 plus an electron. Now, of course, what the technique used by Ray Davis, who was a chemist, a brilliant chemist from Brookhaven National Lab in the US, what he did was to separate out the few atoms of argon 37, as was said, from the 600 ton of cleaning fluid. And that was done by bubbling natural argon in it. And this argon picked up the very small, the few atoms of argon that were there in this fluid. And then these were taken away into and through, purifying agents into a small proportional counter, a very low background proportional counter, and they were counted. So actually this was done over about a month or so, and every month you produced about 10 to 15 atoms of argon 37, which of course took similar about a month or two to decay, and they were counted. So it was a very difficult experiment, and Davis, who was a chemist, had perfected this method. So initially, the efficiency with which this argon was pulled out was about, I think, 70% or so. But finally, he achieved efficiencies of greater than 95%.
Thank you so much, sir. So now we hand over the questioning part to Janmeje and Mr. Go from Swan. They have got their list of questions. Janmeje, please take over.
Hello, can you hear me?
Yeah, please.
You can hear it.
Yeah. Okay. So, what we were interested about is that how will the Indian Neutrino Observatory, this project, how will it be better than the existing projects like the Ice Cube or the Super Kamiokande?
Maybe I should not speak all the time. Satyanarayana, would you like to answer this?
Yeah, you can go ahead, sir. You can go ahead. I'll join.
Okay. So how is it different? So what we propose to do is to build a huge magnetic calorimeter. So it has a huge electromagnet consisting of about 50,000 tons, of course in 3 modules of about 17,000 tons each of iron. So there are iron plates, iron layers, and below every iron layer we have a detector, and then iron layer, detector, and so on. Okay, so the detector basically measures the particles that are produced when the neutrino interacts with the iron. However, the iron has a very important function also, in that it is a part of the electromagnet. As you know, iron is a ferromagnetic material, right? So you can very easily put a coil, pass a current around the iron piece, and it can get magnetized. So in this case, we have huge coils, about 30 millimeters thick coils, which carry currents of up to about 1,000 ampere of that order, and that will produce a magnetic field in the iron of about 15,000 Gauss, 15 kilogauss or 1.5 Tesla. Of course, that's not the average field. The average field is a little lower than that, because on the edges the field is small and so on. But the idea is that this magnetic field enables one to distinguish between muon type of neutrinos and muon type of anti-neutrinos. That is something that Ice Cube and Kamiokande is not capable of. Why? Because when the neutrinos interact with water, either in the form of ice or liquid, they produce muons. Now they can be mu minus or mu plus. Okay, it will produce the new mu will produce a mu minus. The new mu bar, the muon neutrino, will produce a mu plus. That means the positively charged version of the muon. Okay. Now there is no way of distinguishing these in that detector, because The way it is detected is that when the muon moves in water with a speed which is greater than that of light in the water, right? There is a refractive index of water, which is 1.33 roughly. So the velocity of light in water is about 3/4 that of light in vacuum, right? So if the muon, and it's very easy to do that. I mean, a 100 MeV muon will already be of that speed larger than that, right? So, or of that order at least. So we are going to look at about half a GeV, giga electron volts, which means 1 giga electron volt is about 10 to the power of 9 electron volts. So that's about that total energy is about 5 times the rest mass of the muon. So it's certainly relativistic. So it is moving essentially with a velocity very close to that of light. So it's moving faster than the velocity of light in the medium. Then it produces so-called Cherenkov light. So when a supersonic jet moves in the atmosphere, it produces a sonic boom. So this is akin to that. The Cherenkov light comes out in the form of a cone. However, whether or not it is a mu plus or mu minus, it produces the same kind of cone. So you cannot distinguish a mu plus or mu minus because that is proportional to the square of the charge. So minus minus squared is the same as plus plus squared, right? So it cannot distinguish between the charge. What we are going to have is a magnet. So if you produce a mu minus and it's moving in a magnetic field, it will bend. And I think some of you at least would know that there is something called the Lorentz force. So when a charged particle moves in a magnetic field, there is a force which is Q V cross B. V cross B is the vector product of V and B, but notice the Q is proportional to Q. So if it is minus charge, it will be minus Q, where Q is the magnitude of the charge. So the force is in the opposite direction. So let's say I have a magnetic field like this. Muon is coming from here. One muon will bend this way, and the muon of the opposite charge will bend the other way. Now, if you can track this trajectory, then you can tell whether it's a mu plus or a mu minus. And so we can distinguish between that. And so we can measure nu mu separately, nu mu antiparticles separately. That's the idea. This is something unique. No other detector is there of this, at least what we plan to build of this size. There are, of course, there have been detectors which have done this with accelerator-produced neutrinos, but those detectors there are Minos, for instance, that is about 5 kilotons, 5 point something kilotons. We are going to be about 10 times heavier than that. But that's mainly because atmospheric neutrinos are very few in numbers. So we have to build this big detector. It is not out of choice that we are doing it. We have to do it that big.
Yeah.
Otherwise, we won't get enough events. Yeah.
Oh, thank
Does
you
that
so much.
answer your question?
Sorry? Yeah,
Does
Janmesh.
that answer your question?
Yes, sir. Yes, sir. Absolutely. In fact, you have also answered another question
Okay.
that I had.
What is that?
That was that if neutrinos are so weakly interacting particles, then why are we using iron plates?
Ah.
So that has also been answered.
I mean, you have the neutrino has to interact with something. It can be
Exactly.
anything. Okay, but then
Yeah.
secondary particle that is produced, you have to measure that and then infer about what was the particle that gave rise to this interaction.
Mhm.
So it's not a direct detection; it's an indirect detection.
Because you can't detect a particle if it is a neutral particle. So first and foremost is that you need to kind of provide, let us say, enough number of nucleons. I mean, so it could be any material. It could be low density, high density. It could be water. It could be iron. It could be any material. But obviously, iron has a certain distinct advantage of having higher density, and also more important is you can use it to kind of construct a detector in some shape, right? You can make them into layers of let us say plates, you can stack them and so on. So as you said, the first part is to be able to provide enough material for the neutrinos to to interact, and then you actually detect through we will probably see a little later the particles that are produced here, including the muons, which he kind of mentioned, depending on negatively charged or positively charged. So you measure their parameters, namely you measure their energy, you measure their direction, using. I think you have some questions, so we can discuss that a little more. So
Yeah.
the ion here serves double purpose. One is to provide the nucleons for the attraction of neutrinos. So the larger the detector, obviously you'll be able to get a better number of events. And also you use it as a material for producing electromagnet, which is required to measure the momentum of the particles which are produced. In this case, mostly namely muons. Right? Yeah.
Okay.
We'll talk more about when we come to your other questions on the detector itself.
Then, I think now you should ask the question about the atmospheric neutrinos that this setup is designed for. So why don't you come up with
Uh,
your next question?
okay. So I had just another follow-up since Sir was talking about Kamiokande and Ice Cube. So talking about the frequency of events. So are you expecting a higher frequency or a lower frequency of events compared to Ice Cube or the existing other projects?
Well, that is something. You want to take that, Satya?
I think you probably meant to ask whether you will be able to record more number of neutrino events compared to
Exactly,
the.
exactly. Yes,
Okay,
yes.
so it is about the event rate of the neutrinos, but of course you cannot compare directly. For example, you said about ice cube. Ice cube looks at a very high energy neutrinos, extremely high energy neutrinos, which are coming from intergalactic sources. I mean, that is how the detector is designed for. Which means, for example, since they use a cube of, a kilometer cube of ice, so which is actually the material that they use, right, for neutron interaction. So, so that means you actually look up only those. Also, I mean, the fact that they have the detector construction is also such where so you use, instead of using, as Professor Datar mentioned about iron plates, they use there as ice as a material, and the interactions that happen inside the ice and the detectors to record them. We will come probably later for INO experiment, but there they use basically the light that is produced in the interactions are actually measured by photomultiplier tube, something very similar to what he mentioned about the Kamiokande experiments, except that every experiment comes with its own challenge, remember, because in Kamiokande you have a huge tank of water, and so the Charnikov light that is produced, as Professor Datar mentioned, is actually you can record it by huge photomultiplier tubes of the order of about 50 centimeters in diameter, which are kind of embedded into a complete like a cylinder which is housing 50,000 tons of water. Whereas in the case of ice cube experiment, they kind of suspend. It's like a string of photomultipliers along with its all electronics and signals and whatever, all these cables. They lower down kilometers deep by kind of drilling holes into that, and it's like a beads in a string, right? And you lower them, and then the light that is produced is actually picked up by photomultiplier tubes, photomultiplier assemblies, let me say, which are actually embedded into this entire area of a square kilometer, right? What I'm trying to say is that experiment measures a much higher energy spectrum. Neutrinos of much higher energy compared to, let us say, INO, which is lower. I mean, we mentioned about the energies. But if you go into, let us say, Kamiokande, they measure even lower energy neutrinos, namely coming from, let us say, sun and other supernova and other sources. Whereas, as I said, Ice Cube measures very high energy neutrinos coming from extragalactic sources, and INO measures neutrinos coming in our own atmosphere, namely maybe about 20-30 kilometers from the Earth, right? So each of these, there are dozens and dozens of neutrino physics experiments looking at, namely, different sources from where they are produced. So you look at atmosphere, you look at, he mentioned about where Frederick and Ryan measured the actual, discovery neutrino experiment from reactor as the source. For us, it is atmosphere. For Kamiokande, it is the sun. Maybe, like a dune, and he also talked about Minos. Those neutrinos are coming from actual accelerators. You can say man-made neutrinos. So different experiments use different sources of neutrinos, namely, and also they use different techniques to look at these experiments, right? So as we saw, somebody uses water, somebody uses iron, somebody uses photomultiplier tube, somebody, maybe we are going to talk a little bit about gas detectors and so on. It's very important when you do research in such kind of very top rank, very, I would say, a difficult kind of experiments. It's very important that you do by multiple methods and multiple ways of doing it. Then only the evidence for such a new phenomena can be, ascertained very, very well.
Wonderful. Janmejay,
Yes.
you had
Yes.
a set of questions. You all can continue. In between, I'll ask Pratyusha to take her question when the right time comes. You all had a set of.
Okay. So sort of has a question.
Hello, am I
Yeah,
audible?
so my actually, you
Pratyusha
have
later.
already.
I'll call you. Yeah,
Am I
you are.
audible?
Please.
Yeah. So my question, you probably partly answered it. My question was how, I mean, there are neutrinos coming from various sources, intergalactic, say cosmic ray neutrinos coming from sun, that is solar neutrinos. All the neutrinos, I mean, will they interact with iron to produce muon pairs? Because then that will be very difficult to distinguish between those neutrinos. So how, I mean, INO project, how will you distinguish between the different sources of neutrinos, because they all will interact with the irons producing muon pairs, right?
Yeah, okay. So I'll take this question. The solar neutrinos extend from about, from a very low energy of the order of maybe keV or so to about 15 MeV, million electron volts. The ICAL detector at INO will be sensitive to neutrinos above about half a GeV, which is 500 MeV. So ICAL detector will be completely insensitive to solar neutrinos. We just cannot detect them with the detector that we are planning to build. Of course, if you have some other kind of detector, you could detect solar neutrinos. And in fact, I mean, there are some people who are thinking about what to put in the tunnel once it comes out. As Satya said, the ice cube detector with very sparsely populated photomultipliers, because it's just too expensive to put too many photomultipliers like Kamiokande for that kind of coverage in a 1 kilometer cube detector. So the sparseness of these photomultipliers means that you collect only very little of the light. And that means that your so-called ability to detect low energy neutrinos goes away. So their threshold is of the order of tens of GeV. Okay, it is of the order of maybe even higher than that, 100 GeV or so, because they are planning to look at tera-electron volt neutrinos from extremely energetic sources outside our galaxy. And since that is their aim, they can afford to populate it sparsely. Indeed, the whole plan was to build populate them in a very large volume, so that you can have a large coverage area-wise, and you can get still some events per month or per year. Somebody asked, I don't remember, you or the previous questioner asked, how many events will there be? So we will typically have about 3 events per day, 3 to 4 events per day in ICAL with 50 kiloton. Okay. Super Kamiokande, because it is also measuring solar neutrinos, has a much larger event rate. Of course, the total number of interactions in the detector will be much higher, even in ICAL, because even if you go down underground below 1 kilometer of rock, the number of muons, cosmic ray muons itself, is very large on the surface. For instance, our area is going to be something like 16 meter by 50 meter. That's about 10 to the power of 3 meters squared. And the number of muons is about 150 muons per meter square per second. Okay, so you have 1.5 to the power of 5 muons on the surface per second. Now, if you go down 1 kilometer, you go down in muon rate by about a million fold, which means 0.15 muon per second is what we will have. You can see that this is much, much larger than the neutrino events that we are expecting. So you have to find ways of, tackling that background. But we can do that because you can veto it out depending on the signal level seen in the top detectors. And of course, the neutrinos coming from the bottom, they of course are seeing the whole Earth. So there are no muons there. Directly, muons cannot come. So the upward going neutrino events are very clean. The downward going events have to be cleaned up, as I said, considerably. Because 0.15 into 1000 is still about 150 muons per second. That's quite a lot.
Okay. And now we've got a very interesting question from Pratyusha. So the line of discussion, thoda sa we will change. And Pratyusha has got a very interesting question regarding neutrinos. Pratyusha, can you unmute your mic and read your question? Yeah.
Yes, sir. So it is estimated that 68% of the universe is made up of dark energy, and about like 27% is made up of dark matter. So as we know, like I've read about it, that dark matter is like somewhat similar to neutrinos, that like it is like it does not like interact with visible matter. So is neutrinos like related to dark matter in any possible way?
Well, I mean, this is a completely open question. We have absolutely no idea what dark matter is. Okay? And I think nobody in the world has any idea what dark matter is. We will only get clues once experiments which are designed to try to detect these dark matter particles actually detect them. Then we will get some first clues as to what possibly is this dark matter. And that's why this is, in fact, the name goes like that, right? Dark matter. We don't know what it is. But it interacts gravitationally. And so some of the most, strong signals of that are through the gravitational interaction of dark matter. So, for instance, from the velocity spectrum as a function of radial distance from the center of a galaxy, you find that it doesn't go the way you expect. It should have risen and then fallen, whereas it seems to rise, but then it stays almost flat. So there is matter there, which we don't see. It's not luminous. So that's why it's called dark. But people have tried to find out what is that dark matter made up of. Is it made up of elementary particles, just like we have elementary particles of the normal matter that we see, maybe of a different kind, but we don't know. We don't have an answer to that yet. People are looking for it. There have been some experiments which claim to have found some evidence, but they have not been substantiated by other experiments. So the field is completely open, and people like you, if you are lucky, you may be able to find the first evidences for dark matter. Who knows?
Yeah. Okay, that was wonderful. So, I mean, just as a curious afterthought, is it any possibility that neutrinos also could be a part of the dark matter family that is there?
That possibility does exist, but in a way which probably we also, again, there is a big if there as well. If there are the so-called sterile neutrinos, and they have masses of the order of electron volts or a few electron volts, they could account for a significant part of the dark matter. However, we have only smoking gun signals, and perhaps even that evidence might go away with further experiments. Of course, if it survives, that would be great. That would cause a great upheaval in our understanding. And so there are, just like people are looking for dark matter, people are also looking for so-called sterile neutrinos. Neutrinos which are not among the three neutrinos that we know of. So there's a fourth variety. And if there is if a fourth is found, who knows, there may be a fifth one as well. So that comes in a separate kind of study that people are doing, and doing it quite vigorously, by the way. In fact, again, there is one group which claims to have found evidence for that, although there are many other experiments which do not find evidence for such a sterile neutrino. So the field is open. There's a lot of things going on. But as far as if you don't find a sterile neutrino evidence for that, then the masses that we have in place of the neutrinos, they are too small to account for dark matter.
Okay.
Because they are of the order of fractions of electron volts, 50 milli-electron volts or so, and they cannot account, even though they are almost as numerous as photons, the photon background, the cosmic microwave background that we see in the universe of the Big Bang days. So that it still wouldn't account for the dark matter. It's much too much.
Thank you so much, sir. This was a very interesting piece of conversation. We read a lot of, in the popular science section where people like to discuss, and speculate, I would rather say. So a lot of discussion happens on this one. This was really clarified. Thank you, Pratyusha. That was a wonderful question. Janmeja, can we get back to you with the next questions?
Yes, sure. So I had a question that since Sir mentioned that the primary motive of the IONO project is to study the atmospheric neutrinos. So I was going through the material for the IONO project, and I found that it's one of the motives is to study atmospheric neutrinos, while another motive is to also study flavor variation. So what I'm interested in is that since atmospheric neutrinos coming from the top and the neutrinos coming from the bottom, through the Earth, the ones that come through the Earth will undergo more flavor variation than the ones that is coming through directly from the atmosphere into the detectors. So what is the primary motive of this project? Is it to study the flavor variation, or is it to better understand the atmospheric neutrinos?
I think we are not going to learn as much from just studying the fluxes and directional fluxes of the atmospheric neutrinos per se. We will learn much more from the fact that neutrinos oscillate, that they change their flavor. And they change their flavor also in different ways. Okay, for instance, if they pass through matter, there is something called the matter effect. That means the properties of the neutrino get slightly modified. It is something like what a photon encounters in a refractive, material, like glass, for instance. Its velocity changes, right? And in fact, there are also materials where right-handed circularly polarized light travels with a slightly different speed as compared to left-handed polarized light. You're aware of that? I forget the term that is used for that. It is called not refractory, it is some other term. But basically, the speed depends on the
Birefringence?
polarization state. Pardon?
Birefringence? Are you?
That's right.
Birefringence.
That's right. So now what happens is that a neutrino which interacts with the material that it encounters in between, that can modify its properties in such a way that if the so-called mass hierarchy, that means the ordering of the three masses of the neutrino is one way, the muon type of neutrino is affected, whereas the anti-particle is not affected. If the mass hierarchy is reverse, so-called inverted mass hierarchy, then the other way, it happens the other way. The anti-neutrino is affected, the neutrino is almost not affected at all. So this so-called matter effect is the key to our way of understanding or getting a fix or getting to measure the mass hierarchy, the mass ordering of these states. So as I said, there are three types of neutrinos: electron, muon, tau. But you can also represent it by neutrino of mass m1, mass m2, m3, and these are perfectly equivalent descriptions. Okay, but when a neutrino is produced, it obeys the laws of flavor conservation. Okay, so if I have a mu minus, then associated with that, you have a mu bar produced. Okay, and similarly the other way around if you have a mu plus. So while when they are produced as either nu e, nu mu, or nu tau. When they propagate, they since it is a mixture now of these three mass states, these masses will propagate with slightly different speeds. Okay, because they have the same energy. Now, something which has more mass will propagate slightly more slowly. So when you look upon it as a wave, you will see that at a given distance, the composition will change. To start with, it had a certain composition. The nu e had a certain composition in terms of M1, M2, M3. As it propagates, you might get more of M2, less of M1, and maybe somewhat different M3, and like that. But after a certain distance, which is the oscillation distance for that energy neutrino, it will come back to its original flavor. So if it started out as a nu mu, at that place it will become a nu mu. Then again, as it propagates, it becomes a mixture of nu e, nu mu, and nu tau. That's called the oscillation phenomenon. This is a purely quantum mechanical phenomenon. And so if this, and the fact that there is matter can lead to, in certain energy ranges, a drastic enhancement in this oscillation probability. So a nu mu can go away and become a nu e. Okay, so you will get a drastic reduction when you look at nu mu. So that's the idea. So the ICAL is not just going to look at the mass hierarchy, which is of course one of the goals, because as I said, depending on which kind of mass ordering there is, you will affect the nu mu's more or the nu bars more. Okay, but also in actually looking for this matter effect, the so-called resonant matter effects. And that is something that nobody has seen, because this can only be seen when it travels through a large amount of matter. Of course, it has indirectly been seen in the solar neutrinos. That was, in fact, that is how this actually gained prominence. The three scientists called Wolfenstein, Mikhaev, and Smirnov who proposed this, and so it's called the MSW effect. And so the neutrinos that start out as electron type of neutrinos oscillate away to muon type of neutrinos, and so we see a shortage in electron type of neutrinos on the Earth. That is what was the so-called solar neutrino problem. And this was first pointed out through the data of Ray Davis, who got the Nobel Prize for measuring solar neutrinos. And this was solved subsequently by knowing that neutrinos oscillate, but also very directly in the case of solar neutrinos by the so-called Sudbury Neutrino Observatory, where they measured a kind of reaction which is sensitive to all three kinds of neutrinos. So they found that what was missing in electron comes back fully in the full neutrino signal, the so-called neutral current signal.
So now,
Yeah.
a question like which is more broad in nature, that we are observing that a lot many countries are getting into the field of neutrino research, and various types of experiments are happening. What's the reason of so much of an exceeded interest in neutrinos at the present moment?
You see, neutrinos in the so-called standard model, which the last prediction of which was the Higgs boson, and which was detected in 2012 at CERN, the so-called God particle. You all must have heard of it in newspapers, right?
Yes.
And so that was the last big piece that said that, okay, the standard model is the correct model when you want to describe nature. However, there is a fly in the ointment. The standard model has the neutrino mass to be identically zero, whereas we know from neutrino oscillations that neutrinos have mass. At least two neutrinos have non-zero mass. See, there are three neutrino mass states, right? M1, M2, M3. For the oscillations to be seen, and from the other observations of solar neutrinos, accelerator produced neutrinos, atmospheric neutrinos, oscillations have been seen in all of these. We conclude that at least two neutrinos have finite mass, non-zero mass. One could be finite, but the lowest mass could also be zero. it's not inconsistent with the experiment as of now, because we haven't yet observed the scale of these masses. Okay, so now this is already, as I said, beyond the standard model. So neutrinos provide us with a window to what is going to come in future. What is the next big theory to of which, of course, the standard model will be an approximate. In some limit, the standard theory will come about in that bigger theory, but it will also help us understand why the neutrinos have mass, and perhaps there'll be some other theory after that as well, which will try to understand gravity and these electroweak interaction, strong interaction, all in the same framework. And in fact, one candidate for that is the so-called string theory. So this helps us understand and go beyond our understanding right now. So that's why neutrinos are an extremely exciting subtopic. It's probably the fastest moving areas in high energy physics. And they're also the most intriguing, by the way. We know very little about neutrinos. For instance, I was talking about muon, right? Mu minus, its antiparticle is the mu plus. Electron, its antiparticle is the positron. However, we don't know whether the neutrino and the antineutrino are actually the same particle or not.
Yeah.
As fundamental a question as that, even after about 90 years after it was proposed, we don't have an answer. And so there are experiments to actually look for that. So-called neutrino-less double beta decay is one experiment which will hope to answer this question.
Yeah, because there's a lot of interest among the people also. There's been an interesting question that how can neutrinos be potential source of information about unreachable parts of the universe, like the center of the sun. So if a neutrino is coming from the sun, if we get to know more about it, will we get to know more about the sun also?
Yeah, that has already happened.
Yeah.
I mean, the fact that we have detected neutrinos from the sun, solar neutrinos. These were detected by Davis in experiments starting in about 65 or 67 or so. And he measured these for almost 20, 25 years. Very painstaking set of experiments. And he showed that there was a problem. Of course, many particle physicists at that time, theorists, did not believe that there was a problem. Okay? He found, in conjunction with the solar model of Bacall, another very famous scientist who actually Bacall and Davis had proposed that experiment, the chlorine experiment to be done underground. So Bacall was very persistent in refining his model of the sun, which included lots of physics. It included nuclear reactions, the model for the sun in terms of pressure, density, temperature variations across the radial profile and so on. Other kind of excitations of the sun and the data therefrom. So all of that could be understood in a so-called standard solar model. And from there, what was inferred was that the total number of neutrinos expected is about 3 times what Davis was seeing. And the particle theorists said, oh, that's not a big problem. Come on. If you can get something correct to within a factor of 10, you should be happy. You go by, don't worry about this small factor of 3. But it turned out that Bacall was right. In fact, he said that there's something in particle physics that is not understood, and maybe oscillations can help explain this. And finally, it turned out that he was right. And that, in fact, a couple of Nobel laureates have said that, yeah, we were wrong. We were biased against this kind of explanation. Yang, I don't know if you have heard of that, he admitted later that he was wrong and that people like Bacall were right. So, it happens in science. You might have your kind of biases, but ultimately when the facts come out, they go against your bias. That scientist also has to accept it with grace, right?
Yeah. That science could teach the society at large to accept
This
one's.
is a very unique experience. In the words of Bohr, this doesn't happen in many other activities in human activities. Where we accept that yes, we are wrong and that somebody else is right.
Yeah, people are happy to know that they are wrong.
Yeah, that's right.
That is how science progress, right? I mean, you build from the facts that are given by someone else, and many times, as I said before, it's not enough just one group or one experiment kind of comes out with some kind of conclusion. People also want to look at, for example, Datar mentioned about Higgs boson research, right? I mean, it's very expensive to build such a accelerator, and also on top of that, you build many experiments, and you find that exactly identical two big massive detectors were built on LHC with a very similar goals, right? Namely, actually two goals. I mean, one is mainly Higgs boson, but you may ask, like, if the goal is the same, why did you build exactly two experiments? I mean, the kind of physics that one is talking about at that time is, so important to discover Higgs field, Higgs boson. You require two identical massive detectors, each of them having about 7,000, 8,000 physicists. So it's in science it happens. Yes, that's right. You only go by essentially experimental. Physics is always an experimental science, and you need to really look at things in that perspective. So yeah. Negative result is also considered as a result because it rules out a certain hypothesis in some way.
In fact, I'd like to add to what Satya said, namely that if a theory predicts something which can be proved wrong, that's how you make progress, because there is the possibility that you can prove it wrong. If there is a theory which you cannot check at all, you cannot either prove wrong. I mean,
all right.
Then that theory is of basically no use, because it should be you should be able to prove it wrong by one measurement. For instance, Einstein, I think, has made that remark that if, for instance, you find that the velocity of light is not a constant, then I'm wrong. I have to take my theory of relativity and throw it in the dustbin. Right? So that's how it goes.
Wonderful. So, Janmeji, can you all come up with your next question, and then we'll start talking about the broader aspects of the project.
Yeah. So, hi, am I audible?
Yes.
Yeah, you are.
Yeah. So my question was that other types of, I was wondering that other types of neutrino projects, they are at higher latitudes. So the volume or the pressure of atmosphere that varies upon the latitudes. So will our INO based program that will get any advantage or disadvantage due to its latitude, or I mean, will the neutrino flux be a very big issue when the latitude varies? That was our.
Okay. Let me just, if I've understood you right, the pressure actually doesn't change very much with latitude. Okay? We have roughly the same thickness of atmosphere all around. Now, there is a small oblateness and so on, but that doesn't affect the pressure so much. What matters, on the other hand, is the effect of the magnetic field on the protons that come in and produce the pions, which ultimately lead to muons and the neutrinos and so on. So, if a proton comes in exactly in the north-south direction, the magnetic north-south direction, it doesn't get bent, right? On the other hand, if it comes equatorially, then it sees the maximum magnetic field and it will bend away. Okay. So, and this will affect, of course, the low energy protons more than the high energy protons. So, in fact, there is a latitude dependent cosmic ray flux. So, at the equator, the cosmic muon flux, for instance, is somewhat smaller than the cosmic muon flux at higher latitude. However, I think you have asked a good question. Is there any effect at all of the latitude on experiments that you might build? Yes, there is. For instance, if we are very close to the equator, I think latitude of Madura is, I think, 11 degrees or maybe even less than that. Satya might remember a better number, but it's let's say it's of the order of 10 degrees. Okay, just to be, even if it is 8 degrees, let's take it as 10 degrees. That's quite a small number. It's much nearer the equator than the labs in the US, Canada, China, or Japan. One effect of this is that if we were to set up a neutrino experiment to look at solar neutrinos, the neutrinos that emerge from the sun, then we should observe a tiny day-night effect. And in fact, this has been predicted by some of our colleagues in math science. Professor Rajshekaran, we call him the Bhishma Pitama of our INO project, So he has been a very early and very strong proponent of the INO project. Is a very eminent particle theorist. So he and his colleagues have calculated this. So it turns out that because of these oscillations, the sun, as seen through neutrinos, will be brighter in the night than during the day. Okay. If you look at photons, of course, you don't see the sun, so it becomes completely shadowed, right? On the other hand, neutrinos, as I said, pass through the earth just like that. They don't care whether the earth is there or not there. But there is a small, tiny effect, the matter effect. And so this leads to regeneration of the oscillated neutrinos back to the electron type of neutrinos. And I think that effect, if I remember, is about 3 or 4% effect.
2%.
And if you have a detector which is sensitive to that kind of signal, we should see a 4% higher intensity of electron type of neutrinos during the night as compared to the day. And we will be sensitive to that because we are on near the equator, right? So the solar neutrinos, which you might take to be a parallel beam of neutrinos coming, they will pass through the core of the Earth, which is the highest density. And so that will cause a small amount of matter oscillations, enhanced matter oscillations, and it will lead to this. It's a tiny effect because, of course, that the oscillation effect is proportional to the energy of the neutrino energy. And I already said that the energy of the solar neutrinos is very small as compared to atmospheric neutrinos. So the maximal effect happens in atmospheric neutrinos at about between 5 and 10 GeV. And these are only of the order of 5 to 10 MeV. So that effect is much smaller, but it's there. And if we build a detector, some of the younger people, if they can build such a detector, that has other goals as well. It would be very nice to measure such things. So that would the fact that we are near the equator would help in that case.
Thank you so much, sir. Now, a lot of people, for the benefit of a lot of people, I would like to know, can you just sum up in brief the history of INO project? Because even proposing such a huge experimental physics science project in India, and then it sounds audacious, like इस तरह का कुछ इतना बड़ा चीज establish करेंगे और we'll do a science experiment. So can someone just, if you can sum it up, how did we arrive till here?
Maybe start from maybe you should start from not just from the INO project. We should also start from, let us say, 1960s when probably
before Satya you go there, let me also say that Satyanarayana was associated with the deep underground experiment in the Kolar goldfields looking for proton decay. And even before he joined, maybe, I don't know, 15 to 20 years before he joined, there is a very nice discovery made there of atmospheric neutrinos. So maybe Satya will tell you more about it.
Yes, sir.
Yeah, so this is very interesting because for us it is very inspirational to see, for example, Professor Datar mentioned to you about how the muons are produced, and when you go underground, let us say typically a kilometer down, you actually kind of end up, reducing the flux of the events of muons by almost 1 million times and so on. This particular gold mine that Professor Datar mentioned was kind of hub to many cosmic ray and particle physics experiments, starting all the way from 1950s. So what people really did at that moment is initially they kind of tried to look at the muon flux as let us say, if I can say, as a depth, for example, the amount of matter that you have of the rock that is sitting there. So mine offers you such kind of facilities where you go deeper and deeper and set up your experiments and count how many muons you will see per, let us say, unit area per second, and then go deeper, and you can actually get both energy and the counting of the muons. Now people went, they become so curious. They went all the way up to more than 2 kilometers, 2.3 or more kilometers. They found that their detectors actually did not give any counts whatsoever. They did not, the detector did not fire anything to say that you almost got rid of any of the particles coming from all the way from surface down. That means if you really see events like, for example, neutrinos, then they can, I mean, that could be the best site where you can look for such particles which are not like, let us say, charged particles from muons coming in, because you ended up attenuating all that flux coming down. So that was a great what you call result. And then they kind of set up a very, very simple, not one, actually quite a series of experiments underground using those days very interesting detectors called let us say neon flash tubes. These are like small glass tubes, you can say, which are about a centimeter diameter and long pipes filled with neon, the gas. And then you have those stacks of them, you know, in a like a vertical walls, and you look for events which are not coming from surface as you look at, you know, when you look for cosmic muons, but these vertical walls actually saw events coming at a very, very large angle coming from the side, right? And you kind of look at them first, what we call, you know, trigger them by scintillation detectors, which you also mentioned, which will tell you that there's something, a charged particle passing through. And then when they enter these walls of neon flash tubes, they actually emit kind of a flash of light, which you can take I mean, they really used ordinary old cameras, of course, mechanized cameras, but with films, right? So when a particle kind of zip through, let us say, at very large angle and passes through these layers of neon flash tube, and the light that is produced, you actually click, just like you used to click olden days the pictures. And then, of course, you develop and analyze and find out what is the angle at which they're coming and where they're actually, their so-called vertex is meeting in the air or in the rock surrounding it, and so on and so forth. And analyze, of course, also they have a what you call a spectrometer, which basically, again, something similar concept like, you can say INO, but it's a magnet by which you can bend the tracks and measure their momentum. And then they, for the first time, almost first time, I would say, because another group also detected around the same time in 1965 August, they detected the first detection of cosmic ray produced, you know, neutrinos. You can say atmospheric neutrinos were actually first discovered in polar goldfields underground mine in about 2.3 kilometers below. So I mean, India that way is the pioneer in the atmospheric neutrinos. I mean, at least this is what happened way back. So since coming in back, of course, after that, this group, the mine is closed, and the group, you know, had interest to look at, you know, accelerator physics, some of that, you know, top quark, and after that Higgs boson, as he mentioned, etc. But there was always a feeling by Indian communities that we should go back to neutrino physics, where we are very strong about. And this really started about roughly around year 2000. And then people started looking at what kind of detector, what kind of source, you know, basically atmosphere. But then we started looking at what kind of detector we should actually build in order to look for. That is how the so-called magnetized iron calorimeter. So the iron which is magnetized, and then, you know, it's kind of made of a sandwich of detectors, which is like iron plates horizontally placed, and in between each of these plates, you kind of keep a gap of around 4 to 5 centimeters, and you kind of insert, like, you know, how you do in a book rack, right? So these are like alternate layers of iron, which is of course used as source of nucleon, and in between each one of these layers you have so-called active detectors. Active detectors are those which can actually let us say signal the passage of charged particles which are produced in the neutrino. So the atmospheric neutrino enter your detector, and if it decides to interact with one of those nucleons, produce, let us say, muons in this case, and then they kind of pass through, you know, alternating between every 10 centimeter you have an active layer, and those are the points that you will be able to detect them. And if you have magnet, of course, as he said, either you will bend on the clockwise or anti-clockwise, and you can also use the magnetic field that you have to detect to measure the momentum. But you also can measure. This is important measurement in the INO experiment. Is since he said, for example, neutrinos can come from top of the atmosphere or from the other side. If you really want to see whether this particle has actually traveled from bottom of the detector towards the top, or entered at the top and going towards the bottom, then you need to kind of see as the particles, intercepting each of these layers, you should be able to measure like a stopwatch. You should be able to timestamp as it is going down or up, right? Because if you see increasing order, you'll see top to bottom. If it is decreasing order, bottom top. And this is very important to see the direction. And then when you see the the length, the distance that they traveled, as you said, the oscillation probabilities depend on the energy of the particle and also the length that it traveled. So you need to measure both of these extremely precisely in order to able to compute the neutrino oscillation parameters very accurately, which is also one of the goals of this experiment. So the entire detector was conceived, and then the entire R&D to produce those detectors and so on. So it has been in a long journey to be able to perfect this technology. Just one word I wanted to tell to give an idea about how big this experiment. The detectors that we use, so-called resistive plate chambers, which are very planar detectors of about 4 meters square each, which is very thin detectors made of essentially glass, right? So our experiment is going to use a large number of them in terms of area, if I can say. For example, it requires about 100,000 meters square of coverage of this detector. It is something like 20 football fields of area. And maybe the largest such detector deployment anywhere in the world may be about 6,000 or 7,000 square meters. You can see what is the kind of challenge. Similarly, electronics. Similarly, magnet. Electronics requires large amount of channels, because you have to pick up the signals coming from typically about, as you said, 16 meters by 50 meters into about 150 layers of such such a sandwich. So it's a huge challenge. You have to instrument about 4 to 5 million detector channels. So it's a fantastic challenge for the students and engineers to be able to build and do the entire R&D and produce them in the large quantities in the Indian industry. So this is a big challenge. Yes.
And now coming back to the point where it all started, what was the news of the delay? Like, why is this? There's a delay in the INO project, which was there. It wasn't talking. The news item didn't speak about it much.
One of the unfortunately, I must say that the delay did not happen because of technological challenges that you need to overcome, or there is certain building of certain part of the detector which required certain R&D, or of course it requires R&D. I'm not saying it doesn't require, but the problem in the case of INO project, most of the hurdles have come from certain misconceptions about which, in fact, earlier today we discussed quite a few of that. And any reasonably well-read a school student or a college student will be able to understand very well with reasonable conviction that these are kind of things that we are researching on are absolutely harmless, if I can use that word. Okay, but just like in Indian scenario, it always happens. Anything that is little bit looks like mystery, you talk about a particle which is coming from sun, and he just now said, for example, the neutrino can come one side of the earth to other side. These are kind of things one visualizes as if these are some sharp objects which can go through a body and kill you, or such. But that apart, these are easy to kind of quell the doubts, because you go and talk like today we are talking. It's very easy to kind of tell, look, hundreds of trillions of neutrinos are passing through our body. Persons, every one of us have potassium 40, let us say, radioisotope in our body, maybe about 20 milligrams, which will produce 400 million neutrinos per day, probably. I think that is the count. And we are a big source of neutrinos ourselves. Okay, and we are afraid of neutrinos which are coming from sun or atmosphere, etc. But what I meant is these are easier probably to convince people. But if there are other kind of elements or people who might have some kind of other interests, now that unfortunately generates certain kind of misconceptions. And then when such a project, obviously it's a big project, it requires certain work to be done at the site, etc., which requires some engineering activities. It's fine. I mean, one has to look at saying that, okay, what is it going to affect? What is the kind of effect, if any? I mean, these are easy to kind of quantify and calculate and convince people. But somehow, unfortunately, in the Indian context, things went different turns. All these kind of legal battles, legal issues. See, we are scientists and engineers. We only know how to do science and engineering. We don't know how to kind of do these manipulations and try to kind of say something. If you see the numbers that Professor Datar mentioned, these are hard numbers anywhere, right? I mean, there is nothing to kind of cheat somebody. Okay?
True.
But if I can say a word, maybe Professor Datar will also mention. So largely, these delays have been due to, if I can say, any government project requires certain government approvals in order to do a certain civil work and certain other work at the site, and it requires governmental approvals, and we cannot bypass any of those, which unfortunately in turn got swapped by all this which we would say wrong legal hurdles that certain agencies or certain individuals probably thrown at this. And I hope people, especially at the site in Madurai and the whole country, I hope they will be able to get convinced soon that this is completely a harmless project.
So just continuing.
Just one line I want to say. Imagine this is an observatory. It observes, okay, it records something which are already produced naturally in the Earth atmosphere. We are not producing neutrinos. We are not generating neutrinos. It is not a factory producing neutrinos. It is something you look at and observe them. All right? Observation cannot do anything harm to anybody, right? And the fact that human life existed, it actually tells that they're harmless. I'm sorry I took more time, but I wanted
to... It was like the two more questions arise from what you just said. Is that on the news thing, it said that India will lag behind. So which are the countries are our closest competitors in terms of, if we get delayed, who moves ahead, number one? And number two, what should citizens do? Like what should the common citizen do to help the cause of science?
Okay,
so maybe I can answer that partly, and then maybe I can also Satya can also share. Now, I think as I said, the goal of INO is to establish an underground laboratory that will house not merely this particular neutrino experiment, the ICAL experiment, but it will also house, let's say, the Neutrinos double beta decay experiment, for which right now R&D is going on. Then also perhaps a dark matter experiment and other experiments that we have not on the horizon right now, but we know that they can be done. For instance, a very nice solar neutrino experiment based on the indium detector would be fantastic. Actually, an Indian person who was in the US, he had proposed this way back in 1976. It's a beautiful detector concept, but very difficult to build.
Dr. Satyanarayana.
Yeah.
Dr. Vivek, your network is causing some issue.
Oh, my network is gone? You can't hear me?
Yeah, I can go on. And then, now you're back, I guess.
Okay, I'm back. No, so I think there are goals of INO which are very long term. Even if the mass ordering problem gets done by some other experiments, such as Dune, for instance, and perhaps even by the Chinese experiment, this is a completely different way of attacking that problem. So, personally, although we would, of course, like to be the first to measure the mass hierarchy problem, the so-called mass ordering problem. But even if we are the third, that's not a big thing, because any such very important measurement needs to be done by completely different techniques. And so, for instance, who knows? I mean, suppose we get a mass hierarchy which is different from the other two, then there is going to be a fourth experiment also which will have to be done, fourth or fifth experiment. And this happens, is not uncommon in physics, that results, some group gets some results, some gets an opposing result. So that's number one. So, of course, we would not like there to be any delay. We would like to start as quickly as possible. But it's not that 1 year later, the whole project goes fat. No, it's not like, in my view, that is not so, because we have a much bigger goal of setting up an underground laboratory for the next generation of physics people. Just as the Kolar Goldfields experiments which were set up in the early 50s, that led to the discovery of atmospheric neutrinos about 15 years later, and to the proton decay experiment which carried on, I think, up to about 85 or 90 or something. So this also, there are many experiments which can be done underground. So I don't believe that, certainly we should not say this too loudly. We would like all the support that we want to have for, to get this project started as fast as possible. But that's point number one. Number two, as I said, the ICAL detector is not also only for mass hierarchy. We would also like to measure the matter effects, resonant effects. Somewhere it enhances, say, in the neutrino sector, anti-neutrino sector, you don't see that enhancement. This is something that we would like to see experimentally. And nobody has the capability of seeing that right now, because nobody has a magnetized detector. And nothing is also there in the horizon as far as we know. So I think there is uniqueness in this. And so even if it gets delayed by a little bit, we should not worry too much. The younger generation has lots of things to do. And the final thing is that this kind of detector ICAL, we have never built something like this on such a scale. And I think once you build that, the younger generation will have the confidence of doing something on their own of such size. And they won't be scared of big experiments elsewhere as well. They can propose big experiments elsewhere.
True. Now, I think we are crossing the time. We are nearly almost nearing 9 o'clock. The talk has been an hour and a half. And it was like smooth, it was tight, it was packed, and it was amazing. Like there was a lot of wonderful questions and like such lucid answers. These children will always forever be grateful to you all, sir, that you all gave your time to talk to them directly. And it's really wonderful. I would also like to thank Professor Palhalli Vishwanath, who gave me the connect to Dr. Satyanarayana. And this is how we connected. And I would like to end up this session along with the thanks. I would also like to request you all, why don't we have sessions like this, because there are students all over the country who are interested to talk to you all, and it's an experience of a lifetime for these kids when the questions are being answered by people like you all. So if Science Minds becomes a platform, a mediator for the science and the future generation to connect, that's what this whole platform was built upon for.
Yeah, I want to comment. Sorry.
Go ahead.
I want to comment and sort of respond to Ashutosh. Yes, I can actually see there are, I think, a lot more questions I can also see on the rolling display. Then I think we could answer it. And I'm sure there are a lot more questions and inquisitiveness that is coming from your students. One thing I really want to take this opportunity to kind of advertise, I know, actually, I'm not sure if I can kind of, do you think I can share just that one slide where there are, is it possible?
Amitji?
Yes, I just want to keep that slide for a while, which actually has all the.
Yes, sir. Please share it. Share the screen. You can show your.
Can you see now?
Yeah, it's coming. Yes, sir.
Okay. So I just want to say a word or two about this. So these are all the contacts that I have placed on the slide, and I'll keep it for a minute for people to kind of note down. So in case you have any further queries, you can always contact us, contact.us@ino.tifr.res.in, or our INO web page is also given here. It is www.ino.tifr.res.in. We have an excellent Facebook full of activity. We also have a YouTube. I know project is the name of the YouTube. We have Twitter and Instagram presence as well. And we also conduct every Monday at 6 p.m. on the YouTube channel, what you see on the screen. You will always hear something very, very interesting, a lecture by one of the eminent persons in the country and sometimes abroad. Of course, this need not be only about INO. It also, or for example, it's not only about high energy physics, sometimes astrophysics, sometimes nuclear physics, and so on. So it's a nice opportunity for you to kind of, just like today we had some interaction, you can really have interaction with different scientists. I think that is also will be very, very useful. These are actually meant for people like you with a lot of interest in science, and we would like many of you to also come and visit our place. If somebody is interested to visit the place in Madurai, where we have a small lab operating with exactly, it's almost same as what the detector we are actually talking about today, except that it is a very small scale. We actually gave a pet name as a mini ICAL. Okay, the big detector. This is a small detector, but exactly the same detector, same component, same way it works, and so on. It's always open for anybody, any age, students or others. Anybody can come. We'll be happy to host you, show you what we are doing there. And similarly, for many of you who might want to kind of do a summer or a winter internship for, let us say, a couple of months at our facility at Madurai, you're most welcome. Every year, there are at least 20, 30, 40 students come, and they really get benefited. They go abroad, they do wonderful work based on the experience that they gain. So here are many such opportunities for young people, and please feel free to kind of write to us and visit us at Madurai, especially where actually things are happening. And in future, next couple of years, there will be much more activity happening, building what we call engineering prototype of ICAL in Madurai. So it's exciting times for younger generation, and we would definitely want you to be part of this excitement. And as Professor Datar mentioned, the next best exciting things in science, physics rather, is actually neutrinos, now that the Higgs boson is back of our head. So please utilize this opportunity, and we are very much open to host you anytime. So I just wanted to take this a few minutes extra to kind of publicize the contacts and various opportunities for students. By the way, these opportunities are both for science as well as engineering students. So, for example, even if you are an engineering student, there are lots of opportunities to do science. I mean, engineering today we did not discuss much, but very, very challenging, extremely challenging to build components required for such a massive experiment. Yeah.
Thank you, sir. That this gives me more ideas for more such talks and more specific talks, so we can connect with engineering college students who can interact with you all and get the benefits. Thank you so much, Professor Vivek, Dr. Satyanarayana. Thank you so much, Swan. Thank you, Pratyusha and Barisan of Modi School, Siliguri. And thank you so much, DY Patil International University. Amit ji is been relentlessly पीछे लगे हुए हैं to maintain the show out here. And it's like I hate to call the session off tonight, but well, we are way beyond the time. So thank you so much. Yes,
hello, Ashutosh ji.
Yes, sir.
On behalf of Swan, we would like to thank Science Wines for hosting this wonderful session, and I would really like to thank DY Patil International University, and especially Professor Datar and Satyanarayana sir for giving us their time and for sharing their knowledge and their experience with us. It would be great if these pandemic times are over and we can be there in person and see the
Sure.
see the facilities. and meet you people and meet you in person. It would be a great opportunity for all of us at SWAN.
Yes, looking forward to have you there. And actually, all summers and winters used to be buzzing with lots of people like you in the campus. But unfortunately, as you said, we are now in a different kind of new normal. I hope things will happen, open up soon.
Yeah, it happens soon. Thank you so much, sir. We take leave.
Thank you.
Okay.
Thank you. Thank you,
Thank
everybody.
you very much. And from our behalf, also, we'd like to thank Pratyusha, Gorishan, Ghosh, both of you, Sarkar and Janmajay, and Amit. Of course, Harshitosh, you have been a great host, and you are like from the word go, you are continuously up, communicating with us and made a wonderful arrangement. And we hope to see many such faces in the future. And I hope we'll have much brighter days ahead.
Thank you, sir.